right now. But there's just, is that it?
Yeah.
Bill Banger put in the pot.
Yeah.
Feel better.
Gary? You ready? Okay, let's get started. Let me have your attention. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. And actually, we have two speakers, both from the Oak Ridge National Laboratory. We have Dr. Michael Sell and Dr. Jeff Binder. I'm sorry. Mike, they're both graduates of the University of Illinois. Mike received his PhD in environmental engineering and an MS in aquatic ecology, and he's been at ORNL since 1980. And Jeff is one of our own. He has a PhD in nuclear engineering from the University of Illinois and an MBA from the University of Chicago. He spent 13 years at the Argonne National Lab before he came to Oak Ridge last April. The topic of their presentation today is the role of water resources in sustainable energy development. Please welcome Dr. Sell and Dr. Bender.
Well, hello. It's a pleasure to be here. I'm not sure exactly what led me to get the invitation from you, but I'm very happy to be here, and we're going to be starting out with some issues that don't sound like nuclear engineering, but I promise you, with Jeff's help, by the end of this, we'll get back to that topic. You must have some fun with this series too, with watching old dogs like me trying to learn some new tricks, so be patient with me. And I also apologize. I guess my color scheme isn't the greatest. You'll have to go back and look at it on the internet, I guess, if you want to see some of the slides better. But, as I said, we aren't talking about nuclear engineering to start, but we're talking about my favorite subject, which is water resources, and a new spin on it, or a new aspect of it that we're trying to work with Department of Energy and other national labs right now to get higher attention, more important attention, and that is that water resources are essential for sustainable energy development in our country and in the world, and that we aren't paying enough attention to it. So what I want to talk about is why we should worry about water resources in the U.S. and in the world, and why we should worry about water and energy. And then what can we do about it? What are the technology solutions? I'll focus mostly on the first question, and Jeff will transition into the technology aspects on the second one. And the answers to these are important to us because we also believe that the science community, the research community here in East Tennessee, both in our laboratory and near university, can make some big contributions here. I'm sure that if you read the news anywhere, you've seen articles. They're everywhere on water issues. There's a couple of different front pages from Scientific American, from U.S. World News Report, and Civilization, but there's a lot more. I just picked out of my mail something in a magazine called World Arc, which is produced by the Heifer International Project, and it's got articles on troubled waters, and the lack of fresh water threatens the globe by some really outstanding science writers. So a lot of people are paying attention to this. I'm sorry, I guess I'm flicking this as I'm talking. Water is in the news, but why is it in the news? Well, the first issue that I want to emphasize is successful water management is really a question of a balance between water supplies and water demands. And there are a lot of variables on both sides of this equation. I got to put this down. There are variables on both sides of the equation. Water supplies, we get our water from precipitation directly. We get water from surface water runoff from rivers, storage in lakes, storage in ice and snow. We get our water from groundwater and from moisture that's stored in the soil. And more we're starting to pick up water supplies from manufactured water or water that's recycled and reused, treated for new uses. On the demand side, there are consumptive and non-consumptive water uses. Consumptive uses would be municipal and industrial withdrawals, irrigation, and energy production, production and cooling needs, which is sometimes consumptive and partially non-consumptive water use. And non-consumptive uses would be hydropower, navigation, cooling waters, again, flood control, and recreation. And more we have an issue with water demands, including the flows that are needed to protect natural ecosystems. We have a dynamic balance between supplies and demands, and energy affects both sides of this equation. And where we're trying to emphasize more attention is needed is that we have to understand where energy enters both the demand side and the supply side, and plan for it. If we don't, we may lose the security of our energy systems. Some facts about water use. These are fairly sobering. See if I can get the pointer working here. Okay. So the first bullet here, of the 1.4 billion cubic kilometers of water on the planet, 2.5% of that is fresh, and less than 1% of that is usable fresh water. So we don't really lack for water, we lack for usable fresh water, accessible, reliable, usable fresh water. The human needs for water, second bullet here on the left, range from 5 to 50 liters per day. And on the low end of that range, that's a basic survival need. Short of air, we need reliable and regular access to fresh water more than we need anything else, more than food, more than shelter. You can only go a couple of days, stop with that toy, without fresh water. If you go for a couple of days, you die. So it's a basic human need on that low end of that range. On the high end, the world that we live in, we use water at a rate of 300 to 100 liters per day to do a lot more than basic survival, washing our cars, watering our grass, things like that, and producing electricity. But throughout the globe, that's the range of individual per capita water needs. 1.2 billion people don't have adequate access to clean drinking water. That is, they're down below this range, they're down in that low end, and what they do have access to isn't healthy. And water availability is threatened in many ways because lots of that supply-demand equation is changing and it's dynamic. And we'll talk a little bit more about that. Other trends in the world that are important is that on the right side, water privatization is a major international trend right now. Private companies are buying up river basins, buying up access and water rights, and using that to both serve municipalities in private water systems and bottling. And bottled water use is growing tremendously. In 1996, there was something like 57 billion liters bottled, and in 2006, 10 years later, we expect that will grow to 143 billion liters. Now, we can solve some of the water shortages problems through water use efficiency. And in the United States, you can see the impact of technology on the graph on the left here. I don't think I'm doing that, but the graph.
Use those arrows now.
Yeah, okay. The graph on the left here shows the increase in per capita water withdrawals and water use efficiency in the United States. And the important point is that around 1970, 1980, we topped out and we've started to decrease through the application of technology the water use intensity in our society. The rest of the world is still down here on the slope where they're increasing their water use. On the left side here, I can't see my own slide, I'm sorry. We have water withdrawals, and they've been fairly flat, total water withdrawals in the United States, but that's not necessarily the case in the rest of the world. The second plot here shows consumptive water withdrawals in the world, 1900 to 2000, and you see a gradual increase in total withdrawals, and again, kind of a leveling out and per capita water withdrawals, but population pressure and increases in standard of living can continue to push that water use graph upwards. Access to water is unequal across the world. What we've got here is a picture that is color-coded by the percent of the population without access to fresh waters, and the darker reds are waters where are countries where the population is more than half of the people have less than adequate access to fresh waters. See the distribution very unequal. We should be concerned when we think about the balance between water supplies and availability that climate change may well affect water availability in many parts of the world. And this is another picture that shows some estimates. This comes from Japanese climate change modelers, but the color scale here on the left is areas where there would be the most changes of water discharge from rivers in a doubled CO2 environment versus current availability. And you can see that even in the southeast United States, there's a lot of red colors, and there's a lot of red colors in the rest of the world. Europe certainly doesn't look very good. Another view of the world. Population growth will aggravate climate changes of water availability because the demand will go up just as the availability is decreasing. This is a paper that was published in Science in 2000 looking at the ratio of availability to, or the ratio of demand to availability under future scenarios versus current base, with the red colors meaning that in the future the demands would increase more than 20% versus availability. And unfortunately, the whole world looks red in this particular case. We all know that there's a lot of uncertainty in climate predictions. These aren't absolutes. They're just one more reason that we should be paying more attention, though, to this water supply balance issue. And even in the United States, there are areas at risk right now. This is another map produced from an EPRI report in 2002 that looks at surface water withdrawal as a percent of available water. That's a similar kind of an index of one of those earlier slides. And the redder and orange parts of the country are the areas where there's relatively less water availability to meet demands. And you can see that even in the southeast, there are plenty of areas that are stressed as much as some of the parts of the west. Most of our attention tends to be focused on the west, that the water problems are just there, but that's not true. The water problems are throughout the country. And one more interesting thing is to think about the fact that the globe is linked through water use. I was at a meeting in January of U.S. and Japanese scientists who work on water problems and climate change, and this slide comes from that workshop. It introduces a different concept of virtual water, which is the water content of the commodities that we trade across the globe. In this case, the blue areas indicate the water content in grains and cereal grains that are transported across the world. The Japanese, at this workshop, is interesting. The Japanese were so interested in water resources, you wonder why. They're a relatively small country, and should they worry about global change? Well, they rely on commodities that come from the rest of the world. If the basic resources needed to produce grains are affected by climate change, they eventually are going to be affected by that, and so they're doing a lot of analysis of these kinds of problems. So water links the globe through international trade. Back in 1996, we did a workshop in Chattanooga during one of the first WUMP summits that was held, and asked questions about what are the R&D needs for sustainable water in the 21st century. And we got not surprising answers, but this is just a list of some of the answers. There are science and technology needs to reduce pollutants and better manage the environment, to increase water use efficiency and conservation, to better treat and reuse water supplies, to do better integrated decision making so we can better plan for all the competing uses of water, and in ecosystem restoration methods, where we've taken too much water out of the natural ecosystem and need to put the systems back together again. But beyond the science and technology needs, the workshop also emphasized the fact that there are a lot of institutional, legal, and educational needs as well. And over on the left side now, the main messages that came out, the middle one is the one that I want to emphasize. One of the participants came up with the slogan that the soft science parts are the hardest parts in water resource management. And what he meant by that was that the things that we know how to do least well are often our institutional reforms, our mechanisms to protect water rights, not just for people but for natural ecosystems and problems like that. And future sustainability of water use will require both social science solutions as well as engineering solutions. So water and energy are inexplicably linked. That's our main message here. And one other statistic is that each kilowatt of electricity that we consume requires an average of 25 gallons of water to produce. And relative to that, that's about the same amount that we use on average to take showers and water our lawns in the United States. So the water content in our electricity is non-trivial. There are becoming more and more water and energy stories in the news, not just water resource stories, but energy-related water stories. And there's a few headlines here. Company ends fight over power generator on New York-New Jersey border. Official plants would use too much water, a water problem in Idaho. That had to do with water use in the state of Washington and the fact that it would affect adversely groundwater supplies in northern Idaho. Another headline, Georgia Power loses bid to draw water from the Chattahoochee. And a fourth, EPA orders Massachusetts power plant to reduce water withdrawals. These are all 2002 stories and indicate that water is becoming a constraint on our energy production. And furthermore, imbalances in supply and demand related to energy are starting to happen. During the West Coast energy crisis in 2000-2001, a big part of that was, or our inability to fully respond to that, was related to the fact that there had been a drought in the Columbia River system, and that hydropower, which normally would supplement energy production in California, was not available. Another reason hydropower wasn't available had to do with endangered species, which is an ecosystem problem, which was constraining energy production. That is, impacts of hydro operation on salmon during low flow conditions. Another example is that moratoriums on energy production and development have occurred recently in several different parts of the country, including our own state. The governor last year had to impose a moratorium on merchant power plants. These are gas-fired turbine systems which have been proposed for development to match or to meet peaking loads during the same time when the energy problems were happening out on the West Coast. And because we didn't know the impact of those projects on available water supplies in our state, governor had to put a moratorium or not allow their development. Similar things are happening in Pennsylvania and New Jersey and then in Washington and Idaho. So throughout the country this is happening. Regulatory constraints on cooling water usage are becoming more significant, and that issue is starting to hit nuclear power plants and relicensing of old nuclear power plants. Over in Europe, during the heat wave that just happened, there were power shutdowns that happened because of the high temperatures and low flows related to that, climate-related impacts. And we're starting to see climate changes that affect the hydrologic regime in many river systems that depend on snowmelt hydrology. Rivers that include high mountain snowpacks and glaciers are starting to see their flow patterns change. In Tennessee, we started a water supply policy panel last year for the governor to start think about what needed to be done to better protect water supplies. That's what this slide is about. Dave Feldman from this university and I served on that panel, and there were a number of recommendations listed here that included collecting better data so that we understand who uses what water, better data so that we understand what water is available, and better regional planning. Unfortunately, the legislation that was proposed was not really passed. This slide is a list of, that I'm not going to read, but a list of the items that were in the legislation that came out of our policy panel, and the bottom line was that some special interests in the state were not willing to accept increased taxes that would have been imposed at the rate of 7 cents per month on the average water user through water utility bills. Special interests didn't want that. That's not very much additional payment. It's a good investment in the future, especially in a state where we don't know who uses water and we're losing information on water availability every day. We have to be more willing, I think, to pay for the information and the data that we need to manage our natural resources. We are starting to build on past activities and to start to address both water resource impacts from climate change and the energy and water issues. I didn't even touch it. I started looking into this a few months ago to see what kind of reports had been done in the past, and on my own shelf I found 1981 Environmental Handbook series on energy and water. That's what the picture is here. But I've been involved in several other recent planning activities, including the 2001 U.S. Global Change Research Program's water sector assessment that looked at the impact of climate change on water supplies and availability. And several other things are happening lately. Here's an example of recent National Research Council reports on water needs. This is entitled "Envisioning the Agenda for Water Resources Research in the 21st Century." That's a report that we're using on a subcommittee on water availability and quality that I'm working on also for the Committee on Environment and Natural Resources under the President's Science Advisor and the Office of Science and Technology Policy in Washington. There's a report that's going to be put together on what the federal agency should be doing right now in water resources under this SLAC subcommittee. And there have been a slew of reports. General Accounting Office, the Council on State Governments, and the Electric Power Research Institute have all put out water-related reports in the last year that emphasize serious needs. I'm going to skip that one and highlight the fact that just next week, DOE, Department of Energy, and the national labs are going to be getting together for a workshop on energy and water. And Oak Ridge is one of about a dozen national laboratories that are getting together with the Office of Fossil Energy, the Office of Energy Efficiency and Renewable Energy, Office of Science. I didn't put it on there, but also DOE's Nuclear Energy Office is involved in that too, and EPRI. And what we're going to try to be doing is convincing DOE they should start up a new program in energy and water. So at this point, I'm going to switch over to Jeff and let him talk about some of the technology options that are available for addressing water supply issues and energy. Jeff Finger.
Thank you, Mike. What I'm going to do is try to just go quickly through a few slides that I pulled together from some other presentations, and a presentation will be made this November at the ANS Winter Meeting on energy sustainability and nuclear's role in that. And I'll try to talk about technology and maybe give you some ideas about where nuclear fits into this picture of this water crisis that really we face globally. The right tools here in the pocket. Technology, there's a number of technology options, and Mike kind of touched on some of those that we could look at and work on to help address some of these water issues. First off, on the supply side, fresh water production from desalination of brackish and seawater, and I'll come back to this, and there's been lots of talk about this. This is actually a very growing area. Desalination is growing. There's more and more desalination capacity installed every year. The Tampa project just got off the ground, and they're desalting there. San Diego has a big project to do that. Many countries are looking very, very hard at desalination options, and in particular using nuclear energy to drive desalination. So I'll talk about that a little bit. So coupling the plants to the future. But what I'm listing here is ways that you can desalt, but I won't get into that right now. On the demand side, though, is not only can power plants potentially through desalination produce water, fresh water, but as I'll say, and as Mike has said, electricity production is a big demand on water. In fact, about 40% of our fresh water withdrawals are for power production. So future plants, we really need to look at more efficient water use for power plants. So more efficient thermal cycles, or air cooling is one option, though there are energy penalties to be paid, something like 15% if you go to air cooling as opposed to, say, evaporative cooling on power plants. Another technology area is water cleanup, and that's improving the process stream exit quality for a lot of water things. So you have water that's produced, say, out of oil and gas operations. Cleaning that water up before it goes back into the water cycle is an important issue. And related to desalination, a big issue, an increasing desalination use is what to do with the brine stream that comes off of the desalting process. So there's new technologies in developing super concentrates, more beneficial uses for concentrates is another area, and also inorganic membranes. And there's a real opportunity right now to bring some of the latest membrane technologies and filtering technologies back to desalting, which is kind of an old technology, and see if we can do it better. Now, longer term, I'm going to talk about this a little bit more. I think we really need to look at an integrated picture of energy, water, and agriculture. Mike touched on the food piece of it. And I'm going to say a word about a 21st century nuclear energy park, or a nuklex. Just quickly, we've kind of hit this before, but again, 39% of U.S. freshwater withdrawals go to power generations, 25 gallons per kilowatt hour electric that we make. Mike touched on siting power plants is becoming more and more difficult. A big reason for that is Section 316 of the Clean Water Act, which basically regulates cooling water structures. It's putting a lot more requirements, and what you're ending up to is a question of how are we going to site power plants. And if you think about that, that's a big issue, because there's an energy policy or an energy plan that talks about building hundreds of gigawatts of new capacity. Well, where are these plants going to be sited? We have to deal with the water issue. So again, newer plants, more efficient cycles. We need to think about that in the Generation 4 concept design. There are some ideas out there with gas reactors in the IRIS design where you may desalt, and I'll talk about one place now is Diablo Canyon where they actually desalt all of the fresh water, desalt water for all the water use at the plant. I don't know if that figure came up before, but so water use impacts can be reduced with better technology. This is an aerial of the Diablo Canyon nuclear power plant, which is on the California coast. It uses seawater for cooling the plant, and it also has a desalting operation, which is located right here, I believe, if I remember right, it was there once, that desalts all the water for fresh water use. But there's an opportunity for technology to look at the discharges and also the intake hose and do that in a more sustainable way with the environment. So again, it's the Clean Water Act, Section 316. The research that we need is to improve biological criteria and designs. I mentioned again the desalting operations that go on at Diablo Canyon. In the 1970s, there was a large desalination program at ORNL. People looked very much in those times at the integration of energy, water, and environment to look at a big picture kind of activity. We need something like that again. We need to go back to that, and that's what Mike and I have been talking about. That desalination program went away, but we need to go back and look at energy, water issues, efficiencies, and economies. Novel plant system designs, materials for water, chemistry, corrosion, heat transfer services, system simulation, INC, multi-stage flash, multi-effect distillation, reverse osmosis. There's a real opportunity to bring new technologies to improve methods of desalting water and also improve uses of water in power production. This is a picture of the RO system at the Diablo Canyon nuclear power plant. Inorganic membranes, I mentioned membranes, again, is an opportunity where new technologies can be brought. Metal and ceramic filters for removal of finely dispersed contaminants, ultrafilters for water polishing, nanoporous filters for removal of microorganisms, even in, as like bacteria and viruses. So there's a lot of new materials and new technology that could really be applied to better water use. I'm just going to say one more thing before I end, which is to try to tie in the nuclear, back to the nuclear piece here. As we mentioned, we need a lot of electricity, we need a lot of power, we have to build power plants to do that, but how you site these plants has got to be resolved with things like water and other energy issues. And there's been a lot of discussion in the last couple of years about restarting our nuclear program in the country, but a lot of the issues that come up are the old issues about the waste, and we talk about the fuel cycle and things. One of the things I would like to kind of leave with you is that we need to step back maybe a little bit and think about the context in which we would actually have a need for nuclear power plants in terms of what is the market that would drive the need for a construction of the plant. And I really believe that if you take a step back and you don't sort of just think about, there's a uranium, which is an energy resource that feeds a thermal energy or a transformer technology that produces potentially not just electricity, but a range of energy products that all would have value. So this could be electricity, hydrogen. Well, I don't know if I'm going to go back or not. Hydrogen, water, process heat, other chemical processing cycles. I think we really need to think about nuclear systems in the future tying into a market driver that has a spectrum of energy products that are coming out of it. and that's got to be a way that we need to be thinking about nuclear in the future. So that kind of brings me to this concept of a 21st century nuclear park, which is really an idea that came out maybe 40 years ago and really came out of ORNL and someone out of Dr. Weinberg, I believe. But I think we really need to go back to look at updating this idea to impact the critical factors for sustainable human development. The potential benefits are significant if you think about energy without CO2, and that's energy that can be produced in a transportable form, electricity, and hopefully in a storable form of hydrogen, fresh water, crop irrigation, energy-intensive chemical processing jobs. I think there's a context that we could be thinking about nuclear systems in the future that present a lot of opportunity for value. So again, there's this market attractiveness, I think, to investors that may invest in these kinds of ideas in the future. Let me talk just for a minute, because I think this ties so much to the nuclear thing, but the international implications of this energy and water thing. The worldwide water shortages are a real threat to U.S. national security and really to global security. Lots of articles written about the wars of the 21st century will be about water, not oil or other things. So there's a real international implication to the kinds of things that we're talking about here. We've been involved in that for the last couple of years. I've been the U.S. representative to something that's called the International Nuclear Desalination Advisory Group. And you'll see a list of countries here that are very much engaged in this activity. And when you talk to people from these countries, what you often hear is, electricity is nice, but fresh water is really what we need. We need some water. So this is another aspect of what we're doing. I think there's active international interest, which could be U.S. opportunities both to market U.S. technology, but also to be good citizens in the world. Weinberg made this observation in 1969 that the ultimate raw material is energy that can be exchanged for almost all the essential raw materials on which society depends. However, energy supply is inadequate and distribution is inequitable. The same can be said for water and for food. So energy, water, and food are really all linked. And so one of the things I think we need to be thinking about is how, that's what we're talking about here again with this water, is the linkage of all of these issues. The solutions have got to be workable in the technical, political, and economic arenas. But the challenges are very immense, but the needs are really very great on this water issue or energy issue or agriculture as well. A couple more things. Sustainable economic development is not possible without ensuring sufficient water supplies. Actions are needed now to ensure that global economic growth can be sustained and quality of life can be enhanced. Again, linked together, water, energy, and agriculture. We think we need a multidisciplinary approach which takes into account regional assessments, realistic power plant siting, technology development to reduce demand and increase supply. Energy system studies would be part of that. And then international collaboration, again, I think is really important to link what we may be doing in the U.S. globally for global and U.S. national security interests. So with that, I'll end the talk.
All right, we have time for questions and comments. Mario?
The Economist magazine has said over and over again that a lot of the water problems could be minimized if water was priced properly so that people didn't grow things like rice in the desert. Do you have any comments on that?
You want to take that one, Mike?
Sure. Although I'm not sure I'm on.
You're fine.
Okay. I don't know your technology here. That's true, but it's only partially true. And this is where the comment from our 96 workshop that the soft parts are hard comes from. Water rights are all embedded in that. And how do you impose different economic structures on top of an established water rights system that that already has over-allocated water to the wrong places. Changes are happening in our country. I think that you have to say that. You are seeing in California water markets develop. You are seeing the cities start to buy out the farmers' water rights, or the farmers willingly sell them if the opportunity is available. But the environmental side of that equation is still really not worked out. Are we leaving enough in the natural ecosystem? That's part of the equation as well. How much does the natural ecosystem need? That's a big unknown right now. So it's nice to say those things, that it's just an economic issue and we can fix it, but it's more than that. It's a lot more than that. And
Keep saying it.
water generally, or agriculture generally, counts for 60%. A rule of thumb is 60% of most water use in various places, and that happens in the rest of the world too. But as we need more, have more mouths to feed and need more agriculture production, you can't afford to just take the water away from them. You can fix some of that with technology, better irrigation systems, but that costs money. So there's some difficult problems, different allocation issues, and human rights kind of issues, source allocation issues to be dealt with in our country as well as the rest of the world.
Okay. Other questions or comments? Larry?
Hey, you made a comment, I don't remember the number exactly, of the water usage per kilowatt hour power generation. It seems surprisingly high. And I guess, is that evaporation, or what is the nature of that usage in production of electricity? Where does it go?
That is probably total consumptive plus non-consumptive use. Some of it is recycled once through cooling, for instance, wouldn't necessarily use up water, but still demands water. And cooling needs are huge.
Right.
I think Jeff said.
Like the life cycle, for example, if you irrigate a crop and it goes into the ground, then the cycle for that to go in the ground and then get back up to surface water again may be a long time. But just passing through the coils of the heat exchanger is seconds, and it's back for use again.
It may or may not be back for use, so the temperature changes.
Yeah, but it's going to be just maybe an hour, maybe a few hours, rather than 300 years.
Yeah,
so I don't know how you'd consider that to be water usage.
Well, you do, because there's a reservoir that's dedicated to the cooling of that plant.
Not necessarily. I mean, it may be. I mean, maybe a river flowing through, or maybe an ocean.
Yeah, but if, say, upstream, you have other people now that want to make demands on that resource that's cooling that plant. I mean, there's an opportunity cost to that water there has to be a volume of water in that system flowing through there that has to be dedicated to cooling that plant, right? So that's a demand on that water that now restricts it from using in other places.
But just using it shouldn't be a really concern. If I drink water or whatever, then it's back in use again.
A few hours. The older you are, the more frequent.
Well, let's say you had a reservoir that was sitting there, and there was that water is used for recreational uses. Maybe it's drawn out for agricultural uses. Maybe it's supply for municipal uses. And now you want to site a power plant there. Now, I mean, that reservoir has to be maintained at a certain level to provide an appropriate heat sink for that facility now. So now you have a competition for that body of water. So that's why total withdrawals is an important number to keep in mind as well.
Okay.
Your observation that statistic is hard to interpret is right. It is hard to interpret, but the point we're trying to make more with it is that there are a lot of interconnections, and energy does require water, and you can't assume that the water is always going to be there. We're making policy decisions on water availability right now in Tennessee's reservoir operations study, for instance, that may well affect the operation of the Browns Ferry nuclear plant during some intense warm or dry periods, because we're going to require the reservoirs to be held higher. That cold water that comes out of Norris and eventually is routed downstream to help cool Browns Ferry may not be available anymore in the future, and that will change, if not the total energy output, the economics of that project.
It seems like the thing that I would worry about more is like pulling down the aquifers for agricultural purposes. In several parts of the country, we've pulled down aquifers to the point where they may not even be useful for agriculture, and that to resupply the aquifers is hundreds of years. And whereas the river flowing through is a very short-term thing. It seems like that ought to be delineated.
Yeah. Another interesting example of where we could make some bad assumptions in energy planning is that we assume we could maintain support a hydrogen economy in part through solar energy and hydrogen production in the sunny parts of the United States. Well, a lot of those are out west. They would depend on groundwater, and hydrogen production could be a tremendous new sink of consumptive water use that would compete with agriculture, that may not be available, would compete with cities, and we need to be worrying about those issues, and that's one of our points.
Yeah, the estimate was to switch the whole transportation sector to hydrogen. A hydrogen-based fuel would be an additional 3 to 5 gallons of water per day per capita.
Burn hydrogen, you get water again.
Somewhere else.
Somewhere else.
This is related to the question of 25 liters. Does that include hydro?
I don't know. That number is a coal and nuclear power plant.
Beware of
Steam
statistics.
cycle. Steam cycle. And they're a little bit different for coal and nuclear, but it includes the water for mining and.
Okay. Any other questions or comments? Well, obviously we have a lot of new faces today, and you may not know, the new people may not know that we do have refreshments downstairs on the second floor, and everyone's invited. But before we adjourn, let's express our appreciation to Mike and Jeff for their presentation today.
Drink beer instead of water. That's something I was doing. Drink beer instead of water. Cities are going to who needs water? And
yeah, that's fine.
it's okay. Hey, how are you?